Hello and welcome, class, to the last section, the last lecture part of Chapter 9 in Burge and Overby's Chemistry Atoms First. So the last reaction type that we have to talk about is what is known as the redox reaction, which is a combination of oxidation and reduction occurring in tandem. So let's get into talking about what that's all about and how we work with these types of redox reactions. Alright, so a redox reaction is always a combination of reduction and oxidation. Oxidation is a reaction that will result in a loss of electrons for one of the species present, and reduction is going to be the result of the gaining of electrons in the chemical reaction. So we can think of these almost in parallel to the acids and bases that we just talked about, where an acid lost H+, a base gained H+. Oxidation and reduction pertain to losing electrons and gaining electrons. This explains why they always occur together in some type of redox reaction, in much the same way that neutralization reactions require an acid and a base to be present. In the reaction that we are seeing to the right, what is occurring is there was at least initially some HNO3 present, and we put in a copper penny. This copper penny is going to end up interacting with the HNO3, going into solution as copper 2+, and the HNO3 is going to decompose, creating NO2 gas. So one of these species is losing electrons, meaning the copper, as it is turning into copper 2+, has to be losing electrons. The HNO3 is going to be gaining electrons, which is what allows it to completely change phase, going from this aqueous acidic state into this brownish gaseous state. Now, the redox reactions we are going to be working with, at least to start, are going to be a little bit easier than what is occurring in this diagram, but what I wanted to point out in demonstrating this is there are a large number of reactions that we, let's say, might have already observed, but we just haven't thought about in the sense of it being a redox reaction. So gaining and losing electrons might seem, maybe it's not, but it maybe seem a little intimidating at first as we start getting into the natures of oxidations and reductions. But just kind of keep in mind that we've probably already worked with reactions like this, either in lab or on paper, and they weren't intimidating before, so don't let them get intimidating now. Alright, so we're going to break down this discussion into 3 different parts. The first part pertains to studying oxidation numbers, and what these really are, what the oxidation numbers keep track of for us, are where the electrons are on the species. We can think of oxidation numbers as a means of electron bookkeeping. So once we know where the electrons are, we can then next ask ourselves, well, will the reaction actually occur? In order to answer that question, we need to look at what is known as the activity series. The activity series helps us to predict whether or not a combination of a certain reduction and oxidation, when partnered together, will actually move forward as a redox reaction, because a redox reaction needs to result in a stable product for both the thing that undergoes reduction and the thing that undergoes oxidation. If it's unstable for one when partnered with the other, no reaction is going to occur. Last but not least, once we know where the electrons are and we have confirmed that a reaction will move forward, at least in parentheses, if it's not told to us that the reaction does move forward, we then have to observe how to balance this reaction. Now, balancing redox reactions can be simple and straightforward, as can be seen in the reaction that is illustrated here down below, where there's 1 copper on the left, 1 copper on the right, 2 hydrogens on the left, and 2 hydrogens on the right. But balancing redox reactions can actually be a little bit trickier than just balancing the elements that are present. And the reason why pertains to the charges that we can see in the reaction. Now here, there are 2 plus charges on the left-hand side, since there are 2 H pluses, and there are 2 pluses on the right-hand side because the copper has a 2+ charge. But just like how we need to add stoichiometric coefficients to balance the atoms that are present, we're also going to have to add some stoichiometric coefficients to balance these charges, as we can kind of see here. And the reason why is that charges are the result of missing electrons. And we know, as we have just previously defined, that redox reactions pertain to electrons moving from one place to another. So we need to make sure that we are keeping track of where the electrons are, as well as where they're going. We need to make sure that these charges are balanced in our chemical reaction, as well as the elemental species. Now, to make sure that the reactions always end up balanced, we are going to be learning a method to make sure that we are keeping track of the atoms as well as the numbers of electrons, known as the half reactions method. So let's start with our oxidation numbers, then we are going to talk about the activity series and wrap it all up by balancing a redox reaction. Okay, well, in order to determine what the oxidation number is on a certain elemental species, we are going to be learning the hierarchical rules of oxidation numbers, or ONs. Oxidation numbers. All right, so the reason why we break down the means with which we determine oxidation numbers in these hierarchical rules, or at least as we refer to them as these hierarchical rules, is because rule number 1 is the most important. There. Want to make sure I'm spelling my words correctly-ish. So our first rule will be followed before the second rule, and the second rule will be followed before the third rule. And the reason why this is important, again, why we define these in a hierarchical manner, is because sometimes these rules will conflict. Sometimes there's going to be one rule that says to do one thing, and another rule is going to say to do something else. How do you know which way to actually go? The one that is listed up on top is going to be the most important. So if in the event, let's say rule number 2 and rule number 5 conflict, you will follow the rule that is on top. You would, in that hypothetical case, follow rule number 2. All right, so let's break down each of these rules, give a couple of examples, or an example at least, of like what the rule is pertaining to and how they can be used to find the oxidation numbers on species. Rule number 1 states that each atom in a free element has an oxidation number of 0. So this rule is pretty straightforward, and in order to assign an oxidation number of 0, we must identify what it means to be a free element. Well, a free element is one that exists neutrally and not in a molecule with other elements. It cannot be with other atom types. So for example, titanium, neutral, not present in any type of compound. This would have an oxidation number equal to 0. Or let's say bromine 2. Each of these bromines is technically, yes, in a molecule with the other bromine, but they are both of the same element type. Because they are of the same element type, they are going to be sharing electrons perfectly equally, which means that their oxidation numbers individually will also be equal to 0. Each of the 2 different bromines inside of this molecule will have the same oxidation number, and the only way that they can have the same oxidation number, which kind of pertains to ionic charge, is for them to have an oxidation number equal to 0. All right, speaking of ionic charge, rule number 2 states that oxidation numbers of ions are equal to the charge of the ion. So oxidation numbers, as a brief aside, are to ionic species as what formal charges are to covalent species. A formal charge will tell us what the distribution of electrons are inside of some type of covalent species. Oxidation numbers do the same thing, but they assume that everything exists ionically, even molecular species. The assumption here is that they will exist with some number of electrons being transferred from one species to another. Is it a perfect description for how the electrons exist inside of that compound? No. But does this model help us to determine how many electrons get transferred during redox reactions? Yes. So even though it is a little bit of a binary system, in this case we are assuming everything is somewhat ionic in nature, which is kind of incorrect, it is still a useful approach for determining how many electrons get transferred during redox reactions. All right, so back to our hierarchical rules. The oxidation number of an ion will be equal to the charge of the ion. So hypothetically, like let's just pick out a cation and an anion. So let's say lithium plus versus sulfide with a 2- charge. Well, both of these things are ions, and these ions exist off on their own. And the lithium, which has a +1 charge, is going to have an oxidation number equal to +1. Similarly, this sulfide, which has a 2- charge, is going to have an oxidation number equal to -2. So each of the oxidation numbers here are equal to what the charge is on the ionic species, this ionic element, as it exists on its own. Now we can also take this same approach if we are faced with an ionic compound, like where the ions are actually partnered together. So let's say we're looking at lithium sulfide. Well, since this is some type of compound, an ionic compound, we can break these two things down into what the ionic charges should be, right, as they are balanced inside of this ionic compound. Lithium should have a lithium plus as a charge, and there would be two of them present. The sulfur would have a 2- charge, and we can see that the charges are going to be the exact same as if they just existed freely and off on their own. So if you're working with an ionic compound or even just free-floating ions, the charge on the ion will be the oxidation number. All right, this leads us into rule number 3. The oxidation number of atoms in a molecule will sum to the charge of the molecule. So this can be seen in the ionic compound that we have listed up above. The two lithiums and the sulfur come together to create something that is charge neutral. We can see, right, it has no overall charge. It has no overall charge because two positives, 2 + 1s, added to a -2 from this sulfur is equal to 0. So that's really what rule number 3 is saying. We're just making sure that we're making charge neutral compounds. Or if the thing that we are working with has a charge, let's say a polyatomic ion like SO4 2-, the sums of each of the oxidation states for the sulfur plus all 4 of the oxidation states for the oxygen have to equal -2. Now what these specific values are between the sulfur and the oxygen to give us the total of this -2, we haven't seen their respective rules yet, but we will in a little bit. But because these rules are hierarchical, again, rules number 1, 2, and 3 are the most important rules, and this rule number 3 kind of sets the stage for the next and up and coming rules to make sure that they all work together and that we don't have any conflicts. So, oxidation numbers of atoms in molecules must sum to the charge of the molecule, whether it be charge neutral or whether it be a polyatomic ion. All right, here's where we start getting into rules that pertain to specific ion types. So group number 1, atoms in group number 1 are going to have oxidation numbers of +1, and group number 2 elements will have oxidation numbers of +2. This rule may at times conflict with rule number 1. If when it conflicts with rule number 1, let's say for sodium, just free existing sodium, right? Sodium exists in group 1, so this means it should have an oxidation state of +1, right? Wrong. This sodium exists as a free ion, or free element, right? It's not bonded to anything, it has no charge, which means its oxidation number will equal 0 according to rule number 1. Rule number 4 pertains more to species that exist in ionic compounds. So sodium chloride, this sodium is an ionic species, Now there's going to be some type of charge distribution between the sodium and the chlorine. Rule number 4 is based off of ionic observations. For instance, sodium nearly always has a +1 charge when it's bonded to things. Therefore, a group 1 ionic element is going to have a +1 charge. So the sodium will have a +1 charge observationally according to rule number 4. Since this overall compound has to be charge neutral, this tells us that our chlorine must have a charge of -1 and therefore also a -1 oxidation number. Rule number 4 also pertains to when you start mixing and matching groups from elements 1 and 2 with other elements, either chlorine, like we can see here, or fluorine, which is listed in the next rule. These cations will have their charges of +1 and +2 before anything else. Rule number 5 pertains to hydrogen and fluorine. Now, these two elements are relatively special and particularly finicky. Hydrogen will always prefer to have a charge of +1, and fluorine will always prefer to have a charge of -1. These rules rule number 5, I should say, these rules for hydrogen and fluorine rarely get broken, but sometimes they can. So like, let's say for instance, we are going to make or observe a really rare compound known as sodium hydride. Well, we know from past experience, sodium prefers to have a +1 charge, but hydrogen also prefers to have a +1 charge. Well, how can these two things come together to make something charge neutral if they both prefer to have a +1 charge? Here is the usefulness for these hierarchical rules. In this case, sodium hydride seems to be conflicting between rule number 4 and rule number 5, which is going to have the +1 charge. Will the sodium, a group 1 element, have the +1 charge, or will hydrogen have a +1 charge? Since rule number 4 is listed higher, this means that sodium will get the plus charge, and hydrogen, because of the nature of rule number 3, meaning that everything needs to add up, if we're working with a charge neutral compound, will have to have a minus charge. Is hydrogen stable like this? Definitely not. It's a part of the reason why sodium hydride is such a reactive species and is actually pretty useful when it comes to organic reactions. This means that in this compound, the sodium has an oxidation number equal to +1, and the hydrogen has an oxidation number equal to -1. Hierarchical rules help us to organize in these exceptional cases which rule must be followed first. Sodium's gonna get the plus charge. Hydrogen, sorry my friend, you get a -1 charge, and therefore an oxidation number also equal to -1. All right, rule number 6 states that oxygen is going to have an oxidation number of -2. Oxygen is also pretty exceptional, so we've pulled it out of group number 6 and we're going to give it its own little rule. This primarily pertains to examples when like oxygen is going to be bonded to other group 6 elements like sulfur. The oxygen will take precedence. But let's look at an example of a compound that, let's say, is not necessarily a super exceptional case. Let's look at water. H2O. H2O contains hydrogen and oxygen. Well, hydrogen is in a rule listed up higher, so we're going to give the hydrogen its stable charge first. Each of these hydrogens is going to get a +1 oxidation number. Now, there are 2 of these things present, and the whole thing is charge neutral. So we have to fill in the blank. What is it that the oxygen is going to get in order to make this mathematic statement true? It's going to get a -2 oxidation number. So here we can see an example of, even when following the hierarchical rules, sometimes the elements that we are observing secondary are still going to get a stable charge relative to what they would prefer to have according to the hierarchical rules. In water, we have to consider hydrogen first, since it is listed higher in the hierarchical rules, right? It has more of an oligarchical standing. I don't even think I used that word correctly. I'm not even gonna try. It is more important than the oxygen, and so we're going to give it the +1 charge first. It just so happens that water is such a stable molecule, because even though the oxygen is forced to have a -2 charge, that's what it wanted anyway. So water is a great example of how, again, just to reiterate myself or repeat myself, sometimes we don't have to break the rules. Sometimes all of the rules get followed and the molecule is going to be super stable as a result. So here now we have the last 3 hierarchical rules of oxidation numbers. Rule number 7 states that the remainder of group 7 will get an oxidation number of -1. Rule number 8 states that the remainder of group 6 has an oxidation number of -2, and group number 5 has an oxidation number of -3. Notice that how group 4 does not get mentioned anywhere in any of these rules, right? We have mentioned group 1, group 2, and now 5, 6, and 7 all explicitly, but we didn't really mention group 3 or 4 on their own. The reason for that is because groups 3 and 4 tend to end up being sort of like fill in the gap elements. They oftentimes are considered so low compared to everything else, like why make a rule for them? Because they're always going to end up not really following the rule that they would want. They're always going to end up just having the charge that is necessary to meet the overall charge neutrality of your compound, or the charge that is present on your polyatomic ion. All right, so let's go from 7 to 8 to 9. What's a great example of something, a group 7 element, or something that contains a group 7 element? This would be something, again, like sodium chloride, where group 7 element is present here. Sodium already was stated to preferentially have a plus charge according to a previous rule. Chlorine is going to end up having a minus charge as a result. It just so happens that this is super stable for it, which explains the stability of sodium chloride as it exists as an ionic solid. This rule is also relatively useful for figuring out the oxidation state, though, for other things that contain group 7 elements. So let's look at something that's a little bit more of a special case. Let's look at this chlorine monobromide, ClBr. So this is a compound that definitely does exist out in the real world. It's a fairly reactive species, and we can kind of use our oxidation numbers to explain why. Well, both of these elements are group 7 elements, so we're kind of in the same situation as the sodium hydride example on the previous slide. One of these things will get the negative charge, the other one will be forced to carry a positive charge despite the fact that it's not super stable doing so. So when we're in this type of situation, where both of these elements pertain to the exact same rule, like both of these are group 7 elements, the more electronegative element will win the negative charge. And similarly, the less electronegative element will win the positive charge if it's the positive charge that they're fighting over. So in the chlorine monobromide case, the more electronegative element is our chlorine, right? It's closer to the upper right-hand corner of the periodic table, so this will earn the negative charge, or the -1 oxidation number. The bromine is going to be forced then to end up with this positive charge, even though it doesn't want it. It is the less electronegative element, therefore it will get the positive charge. So this means that, again, our chlorine has an oxidation number equal to -1. The bromine has an oxidation number equal to +1. And the -1 was determined by the nature or description of rule number 7. All right, rule number 8 pertains to the rest of group 6, stating that group 6 elements would prefer to have -2 oxidation numbers if possible. Sometimes, again, this is not possible. So let's return to the previous example of SO4 2-. Well, since oxygen was already mentioned, this is a special case. This oxygen is going to have its -2 oxidation number before the sulfur gets considered, since the sulfur is now considered only in rule number rule number 8. So the oxygen, each of these 4 oxygens, will have an oxidation number of -2. The sulfur is going to be a little bit of a question mark, since we're going to have to fill in the blank with it, and the overall charge will have to equal a -2. According to rule number 3, the total charge on your species is going to have to equal what the sum of the oxidation numbers is. So here now we have a pretty simple algebraic statement where we have to rearrange and find the oxidation number of this sulfur. Our question mark is going to equal +6. So this oxidation number equaling +6 is really far away from -2, and this is actually what helps to define for us why it is that sulfate is a species that will readily undergo redox reactions. You see, the further away an element is from its stable oxidation number, the more reactive it's going to be. All right, and last but not least, group number 5 has an oxidation number of -3. So let's look at something like NH3. So ammonia. In ammonia, we have to consider each of these elements again separately, observing where each of these elements exist on the hierarchical rules. Hydrogen gets considered first, since hydrogen is in a rule that is listed higher. So each of these 3 hydrogens will have a +1 oxidation state. This will be added to whatever the oxidation number of nitrogen is, and it has to equal a 0, since the charge on our overall molecule is 0. Well, pretty fortunately then, when rearranging and solving for this question mark, we find a -3 oxidation number for our nitrogen. And this, or in this case, the oxidation number that we calculate that must be present on the nitrogen matches what its preferred oxidation number is. So this helps to explain why NH3 is a relatively stable species, though yes, in the presence of some type of acid, it will undergo an acid-base reaction, but it's pretty difficult to get it to start to undergo some type of redox reaction because the numbers of electrons each species has in the molecule is stable. It's exactly what each of the elements wants. So in conclusion, these are the hierarchical rules of oxidation numbers. We can use these rules to determine the oxidation number of every element that is present in some compound inside of a redox reaction. So we can use these numbers to keep track of where electrons are coming from and where they are going to by comparing the charges, aka the oxidation numbers, for each of the elements on the reactant and product side. So we'll see more of that in action once we actually get to balancing redox reactions. But before getting there, we have to talk about the activity series, which specifically is used to predict whether or not a metal will be spontaneously oxidized by some type of ion or acid. All right, so the activity series we can see specifically listed to the right. This is equal to table 9.6 in the textbook. And on top of this table, we have listed the element that is the most easily oxidized. So the reaction that is listed, this oxidation half reaction, is more than likely going to occur in the form that it is listed here. The further down we go on the table, the more easily reduced the element will be. So for instance, gold and platinum are very easily reduced. In other words, it's very easy for these things to gain electrons, which means that the reactions that are listed here are more than likely going to be reversed. The reverse reaction is more likely the further down you go on the table. So elements listed up on the top are going to more than likely lose electrons as presented in their reactions, and the further down you go, the more likely the reactions will flip, and the more than likely the metal will gain an electron instead. So we can use these reactions specifically arranged in this activity series table to predict whether or not certain reactions will occur as elements or ions get partnered together. And the definition of the activity series also specifically lists acids, which is like maybe a little bit strange, but the reason why it's not so strange is we can see hydrogen is listed specifically here on the table. So what this tells us is that in this form, hydrogen can turn into H+ and give off 2 electrons as a result. If H+ is present, H+ signifies an acid. So this is what the activity series why the definition includes acid is because hydrogen is seen on the table, and this H+ presented here means that the hydrogen can exist in an acidic form when interacting with these other metals around it. So it's either metal ion interacting with other metal ion or metal ion interacting with hydrogen in the form of an acid. All right, so let's look though at a specific reaction for how we can actually use this activity series and what it means for predicting the spontaneity of a given hypothetical chemical reaction. All right, so here we have a pretty straightforward example problem. We're told that a lump of solid silver is being dropped into a solution of aqueous sodium chloride. Will the silver react? Which element will be oxidized or reduced if it does? So let's just write out a hypothetical chemical reaction to start, and then we can go back to the activity series to see if the reaction's gonna move forward at all. So we are told that solid silver in solid form, is being added to an aqueous solution of sodium chloride. So sodium chloride in aqueous form. These will undergo some type of chemical reaction. Since we know that we are hypothetically working with an oxidation/reduction reaction, because in the wording of the problem, we're told oxidized and reduced, what this tells us is that charges will change over the course of this chemical reaction. Now, since we can observe on the reactant side, we currently have one species present on its own versus one compound. In order to predict what types of products will form, the easiest way to go about this is to treat this reaction like a single displacement reaction, right? Since we have a single species as one of our reactants and a compound on the other, we're going to take this metal and swap it out for the metal that is present in the compound. This means that our hypothetical products will be sodium on its own in solid form, charge neutral, and silver chloride, either aqueous, or if we look at the previous solubility rules, as it turns out this thing is going to act as a precipitate, so it will also turn into some type of solid as a precipitate, an ionic compound in solution. All right, so our question is, does this reaction, as it is written, actually occur? If you were to take solid silver and drop it in salt water, do you see sodium being given off and a silver chloride precipitate form as a result? In order to predict whether or not this reaction moves forward as written, we can turn back to the activity series and draw some conclusions from it. Now, in this hypothetical reaction, we are seeing silver solid turn into silver with a plus charge, and we are also seeing sodium with a plus charge turn into sodium solid, right? We're just observing the two ionic species here. So these are going to be the half reactions, or the portions of the overall chemical reaction that we're going to try and find on the activity series. All right, so let's go back to our previous series. We're just gonna try and find where sodium and silver are listed. So if we start from the top, we're just looking for sodium and silver. Well, here's sodium, and silver, just kind of following our way, is all the way down here. Now the reactions that are listed up on top, again, are more likely to occur in the form that they are written. So if we were to mix sodium and silver together, the spontaneous form of this reaction would be sodium coming together in its neutral state and turning into sodium plus and giving off an electron in the process. As it's giving off an electron, this will spontaneously couple with silver plus, again, since the reactions down below are more than likely going to occur in reverse. This electron with the silver plus will be a reactant more than likely. So silver plus and electron will turn into silver in the solid state. So this is the spontaneous coupling of these two half reactions. Where up on top, the sodium is going to be oxidized. Down below, the silver is more than likely going to be reduced. Sodium will be oxidized because it is giving off an electron. The silver will more than likely be reduced because it is taking an electron, and the charge is being reduced from this +1 to a neutral 0. Well, if we compare this spontaneous coupling to what's actually occurring in this reaction, we can see that this is the species are arranged in the opposite of spontaneous. Right, in this hypothetical reaction, it's actually the silver that's being oxidized and the sodium that's being reduced. Well, according to the activity series, this is not a spontaneous coupling of these two species. Sodium is already stable in this form, and the silver in its solid state is also more stable in this form. So as it turns out, this reaction does not occur. Yes, we can physically on paper write a hypothetical set of products for this reaction, but if we were to physically take a lump of silver and throw it into a beaker of salt water, we would see a lump of silver sitting at the bottom of the beaker and nothing would happen. There is no reaction here. And so which element will be oxidized? Which element will be reduced? Neither. Each of these species, again, exists in a stable form and nothing's gonna happen. So silver will stay silver, sodium chloride will stay sodium chloride, no reaction occurs. Therefore, there's no reason to write any type of hypothetical or final redox reaction. There's nothing to balance, nothing's gonna happen. So we have thus far discussed the hierarchical rules of oxidation numbers, how to determine, in other words, what species has what number of electrons, what the charges are going to be. And we've also talked about predicting whether or not certain reactions will occur based off of the activity series, where the higher something is listed, the more than likely it will be oxidized. The lower something is listed, the more than likely it will be reduced. If you partner a species that is going to be oxidized with something that is going to be reduced, a spontaneous reaction will occur. If you partner something that is already oxidized with something that is already reduced, nothing's going to occur. And this brings us now to the method with which we can balance redox reactions, known as the half reactions method. Now, this method is a step-by-step guide, as I have written here, to balance our redox reactions. And in some cases, these steps won't be necessary. Sometimes redox reactions are pretty easy and straightforward to balance, just like the very first one that we saw on slide number 2 for today's lecture. However, there are definitely reactions that are a little bit more tricky, and so learning these systematic steps for balancing redox reactions is going to be pretty handy. Now, I will disclaim and say, if you are specifically in my class, I will never require you to memorize this. I will also never require you to memorize the oxidation numbers, like the hierarchical rules. These will be given to you on any test or quiz or homework with which you need to use them. Practice makes perfect, and with more practice, the less and less you will need to rely on the explicit rules as they are written, and instead you can just treat them as general guides. All right, so the best way to see how these rules kind of break down is to work through a specific example. Our first step is going to be identifying the oxidation and reduction reactions that occur. And in order to do this, we need to find all oxidation numbers. So that's our very first step in balancing a redox reaction, is to figure out where the electrons are. Once we know what the oxidation and reduction reactions are, like what species is being oxidized, which species is being reduced, we can split the big reaction into two smaller reactions. The two smaller reactions are going to be those that we then actually end up balancing before we bring back together. So we have a large reaction, we're going to split it in two different pieces. We're going to follow the next set of rules all the way until step 7, when we bring everything back together again into one nice big reaction. So here's where most of the work occurs, in the in-between. Once we have split our reaction into two different smaller reactions, we are going to balance all of the atoms except for oxygen and hydrogen. The reason why we balance all other atoms first is that oxygen and hydrogen are special. In redox reactions, the reason why the half reactions method is required in a large number of cases is because the solvent, in this case water, actually explicitly gets involved in the chemical reaction in much the same way it did with acids and bases. So we have to save the oxygen and hydrogens for later, literally the next 2 steps, but we have to save them for later because the water gets involved explicitly. Once all other atoms are balanced, we can balance oxygens that are present with H2O, again, our solvent explicitly getting involved in the chemical reaction. We can balance the hydrogens also with H+, meaning that, or what this signifies is that in the half reactions method, most of these types of redox reactions must occur in some type of acidic condition. Now, redox reactions can occur in basic conditions as well, but that balancing method requires 1 extra step, and we're just gonna save it for the spring, right? We're learning enough right now. Step number 5 then is once all atoms are balanced, we must balance charges with electrons. So here's where the electrons are specifically going to come into play when it comes to balancing these types of redox reactions. Since the electrons are shuffling around, we need to figure out how many electrons are moving where. Second to last but not least, once we have all of the electron or charges balanced with electrons, we are going to scale the half reactions, so each of these 2 individual pieces, so that the coefficients in front of the electrons match. So these are going to be the actual explicit balancing steps. Once we have the coefficients of the electrons also matching, we can add everything back together. Step number 7 is going to be to take these 2 half reactions, add all of the reactants to one side, add all of the products to the other side, and there you go, you have your balanced reaction. All right, so step 1, we have to find oxidation numbers. Steps 2 through 6, we're actually balancing the 2 reactions. Step number 7, we put them back together. All right, so let's see this in action. Again, it's one thing for me to like lay out the rules, but it's another to actually see them in motion. So let's learn how to balance the following redox reaction using the half reactions method. First and foremost, let's assume that the following reaction is spontaneous, so there's no need to go back and observe any type of activity series. We're just going to assume it's going to go. We need to balance this chemical equation before using it in any type of like stoichiometric calculation. So how do we do this? Well, we can double check first to see, is this going to be easy to balance? If so, we don't actually need the half reactions method. Well, it looks like there are 2 iodines on the right-hand side, 2 iodines on the left-hand side, 2 chromiums on the left, 1 chromium on the right, and then oxygens present on the reactant side when there are no oxygens present on the right. Like, this is a huge red flag that balancing this equation is not going to be as straightforward as one would hope, and that we are going to need the half reactions method. This oxygen present in the polyatomic ion of the, like, what is this, perchromate, I think is what it is, the Cr2O7 2-. This tells us that the solvent is explicitly getting involved in this redox reaction somewhere, and so we're going to need the half reactions method to figure out exactly where the waters are going to be. All right, so rule number 1, we're going to come back here. Rule number 1, identify the oxidation and reduction reactions and split the thing in 2. In other words, we're going to get some good practice finding all of the oxidation numbers in this species. Now, what I am going to do is give you guys what the oxidation numbers are, but I'm going to heavily encourage you to go back and review the hierarchical rules to see if you can't, from start to finish, figure out what all of the oxidation numbers are. So please pause the video now, see if you can't determine what each of the oxidation numbers for iodine, chromium, and oxygen across the board are, and then unpause the video and see what values I am going to supply to you. All right, welcome back. I'm going to give you what the oxidation numbers for each of these elemental species are across the board, and if anything differs from your predictions, please go back and either double check the rules or shoot me a question somehow, either in the comments down below or an email if you're actually in my class, and we can figure out exactly like where the confusions are. So the oxidation number of I- is -1. The oxidation number of the chromium in this particular form of a chromate ion is +6. The oxidation number of the oxygen is -2. Oxidation number of chromium is +3. And the oxidation number of each of the iodines in I2 is 0. So now that we have the oxidation numbers written out, again, if any of your numbers differ or if there's a little bit of confusion still, like, please give yourself a chance to digest the hierarchical rules and come back to these specific oxidation numbers. But for now, we are going to take these oxidation numbers and keep moving forward with the balancing of this redox reaction. All right, so the purpose of finding what the oxidation numbers were to specifically pick out where or how the oxidation numbers are changing for each species from reactant side to product side. So we can see that the chromium is going from a +6 to a +3, and the iodine we can see is going from a -1 to a 0. Now the oxygen is not present on the product side, and so we can assume that the oxygen, again, that will be on the product side is in the form of water. And as we've already seen, the oxidation number of oxygen inside of water is a -2. So we are going to assume that the oxygen's oxidation number is not going to change. The question is, which of these two species is oxidized and which is reduced? The one that is oxidized will become more positive. Because by definition, something that is undergoing an oxidation reaction is losing electrons. And if something's losing electrons, it has to be gaining positivity. The species that is undergoing the reduction reaction will become more negative. And that is because in order to undergo a reduction reaction, you are gaining electrons. And gaining electrons means that the species is becoming more negative. So by comparing what is happening in the reaction, we can see that this iodide is going from, again, this -1 to a 0, meaning that it is becoming more positive. The iodine, let's see, is becoming oxidized. Similarly, the chromium, which is going from a +6 down to a -3, it's becoming more negative. This is the thing that is being reduced. The chromium is being reduced here. All right, so the entire purpose, again, of finding these oxidation numbers is to identify what is being oxidized, which is being reduced, and now we have a better idea for how to split this reaction down into its two core pieces. The first reaction is this chromium Cr2O7 with the 2- charge turning into Cr3+. And I'm going to drop the phases, at least for the meantime, just to save on some space. But bear in mind that the phases are still important. They're still implicitly there. I'm just not writing them because they are illustrated still or shown up above. All right, so the first piece is this chromium piece. This is the reduction piece. The second is the I- turning into I2. And again, I'm just dropping the phases now. They're still implicitly present. All right, so we have now completed step 1. We are moving into the balancing steps. So we're going to balance all atoms that are not oxygen or hydrogen first. So the things that we're going to balance here are the chromium as well as the iodine, since those things are the only things present that are not oxygen or hydrogen. So we're going to balance these elements in the exact same way that we've learned before. In the first of our half reactions, we can see that there are 2 chromiums present on the left. There needs to be 2 chromiums present on the right, so I'm just going to put a big ol' coefficient of 2 right there. And similarly, in the iodine half reaction, there are 2 iodines on the right. We need 2 on the left. I'm just going to slap a big ol' coefficient in front of that iodine. And that is step number 2, right? So step 1 may have taken a while, but the actual balancing steps, once you get into the rhythm of what you're looking for, can pass pretty quickly. Next, we have to balance oxygens with waters. So here's where we're finally going to address the fact that this chromate ion has like 7 different oxygens in it. these 7 oxygens will be balanced or countered on the right-hand side of this half reaction with 7 water molecules. And the reason why we need 7 water molecules is because we need 7 oxygens to be present on the right-hand side. These will balance out all 7 of the oxygens that are present in the chromate. In the second reaction, we can see that there are no oxygens here, and so we do not need to add any waters to the second reaction, right? So sometimes these steps will not apply, and if that is the case, you can just pass right on by. All right, so now we need to balance our hydrogens with H+. Let's return to our reaction and find any hydrogens that might be present. Well, in our first reaction, now that we have added 7 different water molecules, we can see that we have 14 hydrogens present on the product side. This must mean that the hydrogens came from somewhere, so on the left-hand side of this reaction, we are going to add 14 H+. These 14 H+ are meant to balance the 7 waters that are present on the product side. The second reaction, we can see that there are no hydrogens here, so we don't need to apply this rule to the second of these 2 smaller reactions. No reason to balance it with any hydrogens, there aren't any there. Hydrogens have been balanced. All right, so far we've just been balancing the atoms. All atoms, including oxygen and hydrogen, are now balanced, and we must turn our attention to the charges that are there. The charges we are going to balance with electrons. So remember that electrons are negative. Right, let's see, where do I want to write this? Electrons are negative. And so the way that we use them is to bring down the charge of one side so it matches the other. In other words, we want to make sure that the total charge on the product side and the reactant side are equal. And if there is a discrepancy, we're going to add negative charges via electrons to balance everything out. All right, so let's look at the first reaction here. And in fact, I am going to, I'm going to erase a little bit again up on top just so I can, I have a little bit more writing room. So give me a moment. All right, so I've now cleared a little bit of extra space. What I am going to do with this first reaction is count up what the total charge on the reactant and the product side are. So currently on the reactant side, we can see we have 14 positive charges. So this counts as a plus 14, as well as we have 2 minus charges, right? Just right here from our counter anion? Yes, that's the way I want to phrase it. So 14 minus 2 gives us a total of plus 12 charges on the reactant side. Now on the product side, currently we can see we have 2 times 3, so plus 6 from the 3 plus charge in these 2 different chromiums, and water does not contribute anything, so we have plus 6 present on the right-hand side. Now again, pay attention to the charges that are present here. We're not looking at the total magnitude of the numbers, we're looking at the charge. There is a plus 12 on the left and a plus 6 on the right. This means that because plus 12 is more positive than plus 6, we're going to have to add some negativity to bring it down a little bit. We want the charges on the left and the right to match. So in order to get the plus 12 down to match the plus 6, we're going to have to add 6 electrons to the reactant side. In adding these 6 negative charges, we're going to bring down this plus 12 to match that on the product side. Right, so we added 6 electrons to the reactant side. The 6 reactants on the reactant side of this first reaction bring down the total charge such that it matches the product side's charge of a plus 6. In the second reaction, it's a little bit more straightforward as to where the electrons need to go. We can see on the left-hand side, we have 2 negative charges, and on the right-hand side, we have nothing. So in order to make sure that the charges are balanced, again, because electrons are negative, we're going to add 2 electrons to the product side of our second reaction. These 2 negative charges from the electrons are going to balance the 2 negative charges from the iodides. All right, so this is how we use electrons to balance charges. We're always looking at the total charge of the reactant side versus the total charge of the product side. When one side is more positive than the other, you add electrons to it to bring the charge down. And you bring it down until the two sides match, until reactants match products. All right, check. We have balanced the charges of the electrons. And now our second to last step, we have to scale the half reactions. We're going to scale the coefficients such that the electrons match. Now, the reason why this step is necessary, the reason why it's useful, and I'm just going to talk as I erase things to make more space again. The reason why it's useful or necessary is because the electrons that are being generated in the oxidation half step have to be used up in the reduction half step. In other words, as one species is giving off electrons, all of those electrons must be consumed by the next step. So we can see in our iodine reaction, we are generating 2 electrons, but the reduction step requires 6. This means that the iodine reaction has to go through 3 different cycles, right? It has to repeat itself 3 times in order to generate the electrons necessary for the reduction reaction to even occur. So in order to signify this with a chemical equation, we're going to have to scale up everything in the iodine reaction by a factor of 3. So we don't just need 2 I minuses, we need 6 I minuses. We don't need 1 I2, we need 3 I2s. And in order, or I should say, and when we bring together these 6 I minuses and generate these 3 I2s, we're also generating 6 electrons in the process. These 6 electrons will get used by the reduction step as they come together with the H pluses and the chromates to generate these products here. So this is what it means to scale up or even hypothetically scale down. In the future, you might see this, a reaction in order to make sure that the coefficients in front of the electrons match. This is because you want the number of electrons being generated by one reaction to be completely used by the other reaction. All right, so that is the balancing all complete. Now all we need to do is put the reactions back together. We're gonna add the two, wrong way. We're gonna add the 2 half reactions back together. So I'm gonna give myself a little bit more space again. All right, there we go, have some space up on top. So now in order to add these reactions back together, what we're going to do is lump all of the reactants together on one side of the reaction arrow, and on the product side, lump all of the products together on the after side, of the reaction arrow. So this reaction then, in other words, is 6 electrons coming together with 14 H pluses, as well as a Cr2O72 minus and 6 I minuses, in order to react together and form 2 Cr3 pluses, 7 waters, 3 I2s, as well as 6 electrons. And the kind of last but not least is if we need to reduce or alter anything because we have some let's say spectator ions present, we can remove those now or scale things up, scale things down as necessary. Well, we can see that we can't necessarily scale everything down by a least common multiple because we have a coefficient of 1 in front of the chromate. Now we can look for spectator ions though, or common species on the left and the right, and the only thing that we have that matches that description are the electrons themselves. Since there are 6 electrons on the left and 6 electrons on the right, we can actually cancel those things out entirely. And what is left, what remains, is the balanced chemical equation for the redox reaction that we were charged with balancing following the half reactions method. All right, and with that is chapter 9 in the books. So we have made it through our discussion of aqueous solutions, as well as solubility and precipitate reactions, acids, bases, and neutralization reactions. And here now we have talked about oxidation, reduction, and redox reactions. So I would definitely recommend getting some practice with the hierarchical rules as well as with the activity series. And here there are a couple of example problems listed. So if you have homework, please double check and do your homework. If you have any questions, please do not hesitate to reach out and ask your questions. And until next time, class is dismissed.